Here is section 3.3. We go to another section. This is about property diagrams for the phase change processes. Okay, this part is important because it allows us to get a general diagram. And this diagram is also useful if we would like to get a visualization of what's really happening. Okay, so we ask a question. We have got a heating curve for the isobaric process at 1 pressure. But how does the heating curve look like if this process is done at different pressure? That means the pressure other than 1 atm for water. Okay, we know that we have got the heating curve for the heating process at 1 atm. But how about different pressure? So we have obtained the curve for different pressure. Okay, this is also the diagram for water. Okay, so these values are only for water. Okay, in general, for different pure substances, those values will be different, but the trend is the same. So we can see that we can get a several observation. At a higher pressure, it boils at a higher temperature. It makes sense because the saturation pressure increases with the saturation temperature. And the second one, this specific volume for saturated liquid increases and the specific volume for the saturated vapor decreases. And this horizontal line would get shorter and shorter. Okay? At a low pressure, this line is much longer, but if you increase the pressure, the specific volume of a saturated liquid increases. Okay? It gradually moves to right, and this point, which is a state of a saturated vapor, moves to the left. So we will get a smaller and smaller line. And finally, it will shrink to one point. This point is what we call the critical point. Okay, critical point. Here, the saturated liquid state would be the same as the saturated vapor state. And this critical point is important, okay? So that's the reason of critical. And we will call the temperature, pressure, as well as the specific volume. Critical temperature, critical pressure, and the critical specific volume. Okay? Well, at the pressure higher than the critical one, there will be no phase change. For example, for this one, we will have no phase change here for P equal to 25 megapascal. And if we connect all of the saturated liquid state, okay, the critical point as well as the saturated vapor state, okay, that means we connect the whole thing, include the critical point as well as this saturated vapor phase, then we can get this line. Okay, and this line is what we call, sometimes we will call it the saturation dome, D-O-M-E, dome, because the shape is a dome shape. Okay, inside this saturation dome is a saturated liquid vapor region. It's a saturated liquid vapor region. Okay, at the left hand side, because the V is smaller, so it's called a compressed liquid region. Okay, you can think of it as, because the pressure is greater, it will compress the substance to a smaller volume. So this one would become a compressed liquid region. Okay, and at the right hand side of the saturation dome, we will have the superheated vapor region, because it is at the right hand side of the saturation vapor line. And this dotted line denotes the heating curve at a constant pressure. Okay, so you should know how to get a rough sketch of those heating curve as well as this saturation dome. Okay, in general, for all kinds of pure substances, it will have this shape. Okay, so this is the TV diagram, T against V. So we have the TV diagram. For PV diagram, this is the shape of it is similar. Okay, and you will see that the heating curve will be a little bit different. It will decrease very steeply, and then horizontal line, and then we will see that it will be a slightly curved line with a much smaller slope. Okay, and at a higher temperature, of course, the heating curve will move up. Okay, at a lower temperature, it will go down. Okay, well, this kind of PV diagram or the heating curve can be obtained by removing some of the weight that acts on the piston. Okay, it will decrease its pressure gradually, and then you can get a heating curve. Okay, so that's similar to the procedure for obtaining the TV diagram. Okay, here we keep the T constant, and we also connected the saturated liquid state, critical points and the superheated vapor state, so it will become the shape like this. This is also the saturation dome. Okay. After that, sometimes we may extend this diagram to include solids. Okay. We will have something like this. Okay. Inside this one will be liquid vapor, liquid plus vapor region, and this line is a liquid line. If you go to the left, we will have a mixture of solid and liquid, and to the leftmost region is a solid region. Okay. At smaller pressure, liquid form will not exist, so we just have a solid plus vapor region here and directly go to vapor. Okay. At a smaller pressure, you can see that the liquid phase cannot exist. If we just heat the substance at a very small pressure inside this region, then we just cross directly from solid to vapor. This kind of process is called sublimation. Sublimation. This word will appear in the next few slides. Okay. And here we also have a so-called triple line here. Triple line denotes the points where all solid, liquid, and gas phases coexist. For water, the triple point temperature will be 0.01 degrees C, and the triple point pressure will be 0.6117 kilopascal. Okay, and these two diagrams just have one difference, is that this substance would contract on freezing, while this one would expand on freezing. Okay, so we get two different diagrams like this. Okay.
Besides PV and TV diagram, we will also have the PT diagram. Okay, here this PT diagram is also called a phase diagram because you can see that those lines would cut the pure substance into exactly three phases: the solid phase, liquid phase, and vapor phase. Okay, you can see that at sufficiently low pressure, okay, that means the pressure below this triple point, we will have the sublimation line. At this region, the solid can be directly transformed into vapor, vice versa. Okay, one example is carbon dioxide. Okay, in 1 atmospheric pressure, the carbon dioxide would change directly from solid into vapor. Okay, you are familiar with dry ice. Okay, should be. And when you put the dry ice inside the room directly, then you will see that this dry ice would turn into gaseous carbon dioxide directly. Okay, and here you can see that this is a stable point. And remember, in the PV diagram, we have the triple line. Okay, however, for the PT diagram, this triple line has been strengthened into a single point. So we will have this triple point. Okay, and here is the critical point. As I've said that beyond the critical point, we cannot distinguish whether the pure substance is in liquid form or in vapor form. Okay, because there would be no such thing called a vaporization. Okay, and if the substance contracts on freezing, then this melting line will have a positive slope. And if this substance would expand on freezing, then this melting line would be a line that has a negative slope. And if we combine the PVT together, then we will get the PVT surface. Okay, it is built based on the state postulates that I've stated in chapter 1. The state postulate states that if we know two independent and intensive properties, then we can fix the state, and all of the properties will be dependent. Okay. As a result, for example, if we know the pressure and the temperature of a certain pure substance, then the state of that substance will be fixed, and all of the other properties will be known. For example, the volume. As a result, we can build something, for example, like the specific volume will be a function of P and T. Okay, something like that. Okay. Because we have two independent variables and one dependent variable, this function, if we plot it in a three-dimensional space, then we will get a surface. Okay. Here, we will have the pressure pointing along the z-axis, volume along the, for example, x-axis, and the temperature will be the y-axis. Okay, and you will see something like this. Okay, the left-hand side will be the one for the substance which contracts on freezing, and the right-hand side will be the surface for substance that expands on freezing. Okay, well, for this PVT surface, you can obtain the PV diagram, TV diagram, and the PT diagram. Okay, but how? For the PV diagram, you just project this PVT surface onto this PV plane, then you can get the PV diagram. Okay. For the TV diagram, you just project the whole PVT surface onto this VT plane. Okay. or you can think that as a bird's eye view, then you can get the TV diagram. For the PT diagram, similar, we can project this PVT surface onto this PT plane, then you can get the PT diagram. Okay? And you can see that if you project in this direction on this PT plane, then you will get the PT diagram like the one I have put in the previous slide. Okay? And note that because this PVT surface actually is too complicated for our actual thermodynamic analysis, we will not use the PVT surface directly. It's just a kind of a theoretical extension that we will sometimes show here. The most frequently used diagram later would be the PV and the TV diagram. For this PT diagram, actually we will not use it so frequently in this course. In this course, the property diagram that we would usually use would be the TV diagram or this PV diagram. Okay? And you will see the usage of these two diagrams very frequently in the subsequent chapters. Okay? So one more thing. Besides using the TV diagram and the PV diagram, we'll also use what we call the property table. Okay? I will show how to use the property table in detail in the next session.